The binomial distribution, which is a discrete probability distribution, is used to find probabilities in which there are only two outcomes or can be reduced to two outcomes. For instance, flipping a coin has only two outcomes, heads or tails. And on a test, a multiple choice question can be reduced to correct or incorrect. And real quick, there are 4 requirements for a binomial experiment. Number 1 is that there must be a fixed number of trials. Number 2 is that each trial can have only two outcomes or be reduced to two outcomes. And these are often referred to as a success or a failure. Number 3 is that the outcomes of each trial must be independent of one another. And number 4 is the probability of success must be the same for each trial. Binomial probability is the probability of x successes in n trials. For instance, if you toss a coin 3 times, what is the probability of getting exactly 2 heads? The binomial formula, or the formula for getting exactly x successes in n trials, is probability of x equals n factorial divided by n minus x factorial times x factorial times p to the x times q to the n minus x. In the formula, probability of x is the probability of x successes. N equals the number of trials, p equals the probability of success in an individual trial, and q equals the probability of failure in a single trial, which is 1 minus p. And the mean is equal to n times p, and the standard deviation is equal to the square root of n times p times q. I've calculated out the probability posed earlier, 2 heads and 3 coin tosses. And you see the result is 3 over 8, or 0.375, which is 37.5%. The issue with using this formula is when n, the number of trials, becomes large. The calculations can become very difficult. For instance, probability of 59 successes in 200 trials. You can see that the factorial computations are huge. This is where, under certain conditions, we can use a normal distribution as an approximation to calculate probabilities. These conditions are: number 1, the problem must meet the 4 requirements of a binomial distribution. Number 2 is that n times p must be greater than or equal to 5, and n times q must also be greater than or equal to 5. So, for instance, if n, the number of trials, is 12, and p, the probability of success, is 0.3, which equals 3.6, a normal distribution should not be used as an approximation. And number 3 is that if conditions 1 and 2 are met, a correction for continuity must be applied. And this means that for any value of x, we must use boundaries. For instance, the probability of 59 successes, which is probability of x equals 59. In this instance, we would use probability of 58.5 less than x less than 59.5. So 58.5 and 59.5 would be our boundaries. Below is a table listing the different probability scenarios of when to add or subtract 0.5. And we're going to go through several of these using examples. Let's say that a certain golfer lands his ball in the fairway 72% of the time using his driver. 3-part question. Number 1, what is the probability that he hits 43 fairway drives in 54 total driver shots? Number 2, what is the probability he hits at most 39 fairway drives in 54 total driver shots? And number 3, what is the probability that he hits more than 41 fairway drives in 54 total driver shots? In this situation, n, the number of trials, equals 54. P, the probability of success, is 72%, or 0.72, and q equals 0.28, which is 1 minus p. And the mean is n times p, 54 times 0.72, which equals 38.88, and the standard deviation is equal to the square root of n times p times q, square root of 54 times 0.72 times 0.28, which equals 3.299. Before we do any calculating, we first need to make sure the question meets the conditions to use the normal distribution as an approximation. It does meet the 4 requirements for a binomial experiment. N times p equals 38.88 and n times q equals 15.12, so both of these are greater than or equal to 5. Since conditions 1 and 2 are met, we need to apply the correction for continuity for each of the 3 different questions. So for question 1, we're looking for the probability that x equals 43. And in the table, when x is equal to a value, we subtract 0.5 and add 0.5 to the value to get the boundaries. So on a normal distribution, we're looking for the probability of 42.5 less than x less than 43.5. For question 2, we're looking for the probability of at most 39. So 39 is included. We want the probability that x is less than or equal to 39. And in the table, when x is less than or equal to a value, we add 0.5 to the value to get the boundary. So on a normal distribution, we're looking for the probability of x less than 39.5. And for question 3, we're looking for the probability of more than 41. So 41 is not included. So we want the probability that x is greater than 41, and in the table, when x is greater than a value, we add 0.5 to the value to get the boundary. So on a normal distribution, we're looking for the probability of x greater than 41.5. Now that we have our boundaries, we can calculate the probabilities. And we're going to do this by taking their values and converting them to z-scores on the standard normal distribution, and use the z-score tables to look up those probabilities. So for number 1, we want the probability of 42.5 less than x less than 43.5. We need to convert 42.5 and 43.5 to z-scores. The z-score formula is z equals x, or a value, minus the mean divided by the standard deviation. So for 42.5, we have z1 equals 1.09. And for 43.5, we get z2 equals 1.40. Looking these up in the z-score table, for z1 of 1.09, we have 0.8621 to the left of the line. And for z2 of 1.40, we get 0.9192 to the left of the z-score. To find the probability between these values, we'll subtract z1 from z2. 0.9192 minus 0.8621, which equals 0.057 or 5.7%. So there's a 5.7% probability that the golfer hits 43 of 54 drives in the fairway. Now for question 2, where we want the probability of x less than 39.5. Again, we first convert 39.5 into a z-score, which calculates out to z equals 0.19. Using the z-score table, we get 0.5753 to the left of the z-score, and this is the probability. So there's a 57.53% probability that the golfer hits at most 39 out of 54 drives in the fairway. Now for question 3, where we want the probability of x greater than 41.5. Again, convert to a z-score, which calculates out to z equals 0.79. Using the z-score table, we get 0.7852 to the left of the z-score. But we want the area of probability greater than, to the right of the line. Since we know that the total area under the curve is equal to 1, we can subtract 0.7852 from 1 to get the probability to the right, which equals 0.2148. So there's a 21.48% probability that the golfer hits more than 41 out of 54 drives in the fairway. Alright, ladies and gentlemen, you got to put those drives in the fairway. That will keep your scores down. And that be the basics on the normal approximation to the binomial distribution. Hopefully this video helped you out. I do have more videos right there for you. Till next time, I am out of here.